Hey guys, BuildZoid here, and today we are going to be taking a look at the MSI Z490i Unify. So yeah, basically the ITX Unify. I'm really not sure, well, I mean, if you see the name in text, it's fine, but it just sounds weird when you say Z490i, right? Anyway, yeah, so this is MSI's only Z490 ITX board. It's about $270, and I think it's really cool from an overclocking perspective because, yeah, they've done a lot of like overclocking focused stuff with this board, and it's still, even if you're doing like a normal build, there's still a lot of sort of normie stuff on the motherboard. So let's get into it. Starting off with the rear I/O, we've got 2.5 gig Realtek LAN, Wi-Fi 6, and Thunderbolt 3, and that's the normie parts of the board in my opinion, right? So yeah, you've got Thunderbolt 3, and then of course you've got some display outputs over there. There's also a clear CMOS button, and in my opinion, not enough USB ports. However, I can totally understand why there's only 5 USB ports on this, because if we look at the motherboard and, like we have this vent hole right here, which is for the VRM cooling fan, but the thing is like, so you might be like, oh, but couldn't you squeeze a USB port right there? Well, no, actually, because this chip lives right there, and that there is the Thunderbolt 3 chip. So it was either more USB ports or Thunderbolt 3. There's not really any way they could have fit both, because at this point the board is running out of PCB space. Right, like that's one of the biggest problems with ITX boards is just they're very small, and therefore you can't do things that take up a lot of space, or really things that take up any space at some point, right? Because it doesn't matter so much what exactly you're doing, it's just like there's not that much space to start with. So yeah, there's just nowhere to squeeze more USB ports on, but yeah, still 5 USB ports for an ITX board, that's actually pretty acceptable, because most ITX boards aren't exactly like, well, like, actually, I'd consider that, like, very acceptable. Like, most ITX boards don't really manage to squeeze in many more USB ports than this anyway, and you do get the Thunderbolt 3, which is pretty cool if, you need that functionality. And then, and then on the board itself, MSI's done a lot of overclocking focused stuff. So obviously that starts with the clear CMOS button. Unfortunately, there's no Q flash on this board, so there's no, like, recovery options for the BIOS other than, like, connecting a BIOS flash, like BIOS programmer to the board and then programming the BIOS that way. But yeah, you do get a clear CMOS button for overclocking. You also get troubleshooting LEDs over here, and because there's so little space on this board, these are actually properly spaced out and very legible compared to the ATX boards where they're right next to each other and just look like one. Like, yeah, so I'm actually a big fan of this LED arrangement, even though it's still all, like, they're still single color, but at least they're further apart, so it'll be easier to tell which one's lighting up if you're, if you don't put your face right up against the board. And then other than that, we've also got a hole in the CPU socket for putting K-type thermocouple probes through so that you can measure the, so that you can measure the temperature of like the back of the CPU, because one of the problems when running liquid nitrogen is that the temperature sensors, they don't work when you go too low in temperature. And so if you want to get a temperature measurement, so you have like one temperature probe inside the LN2 pot, but if something goes wrong with your mount, like your thermal paste or something like that, well, you're not going to have any idea what temperature the CPU is actually at. And your LN2 pot's going to be telling you, yeah, your temperature's fine, but the CPU is potentially going to be running really, really hot. And so this right here allows you to basically potentially like just glue a thermocouple to the back of the CPU, and you can get a measurement that won't tell you the exact die temperatures, but will tell you like, hey, you have a major problem with your mounting or your thermal paste, which is why we have that hole in the socket. So that's for extreme overclocking right there. Then we've got only a single 8-pin power connector on this board, which you can't fit 2 8-pins or an 8-pin and a 4-pin on an ITX board. But what I'm not a fan of is that MSI is using the standard current variant of the connector. And the reason why they do is like they use the standard current connector on all of their boards. And on their ATX boards, they just give you extra power connectors if you're, if you're on a high current platform. But the thing with this ITX board is like, this is ITX. You can't have a second 8-pin power connector. And 10900Ks are fully capable of maxing out a single 8-pin power connector like that. So while it is kind of unrealistic that somebody would have enough cooling in their ITX build to run a 400 watt, like, well, the CPU would be pulling somewhere around 350 watts, and then you factor in like VR. Well, actually, no, CPU would be approaching something like 370 ish. Because then, of course, you have the VRM power losses, and then you actually get the power that the 8-pin is providing. But that 8-pin is only good for 384 watts, and I've actually managed to get a 10900K to pull, close to 400 watts on ATX motherboards. And admittedly, I was at the absolute limits of the cooling system at the time, but if you were doing a really like ridiculous ITX build, you might actually end up in a situation where that 8-pin power connector would be technically overloaded. Now, given some airflow, that's actually fine. But yeah, I would have preferred if they had used the high current variant of the connector. At the same time, this is kind of a rather unrealistic scenario. And if you're only doing like burst workloads, then it's not actually a problem. It's like the concern there is that if you were running, the CPU 100% load for multiple hours, that connector would actually potentially overheat and melt. But again, like, you're going to be very thermal. Like, for most, like, you'd need to be not thermally limited on the CPU for that to be a realistic scenario. But and you can get very good cooling on a 10900K, because you can get a giant water cooling loop, liquid metal on top of the IHS. If you're really adventurous, you can actually also put liquid metal under the IHS, or even go as far as going direct die. And then, yeah, you'd be totally capable of just like massively overloading the 8-pin, and I would have really preferred the solid, like the high current variant. But again, that's like a 1%. Actually, probably not even 1%. It's probably like a 0.1% scenario that somebody would have that good a cooling system on their 10900K in this motherboard. And if you're running the motherboard, like, because the board is designed to, do some LN2 overclocking, like, if you're running on LN2, the whole board is going to freeze through. Your benchmarks don't last more than like a couple minutes. The 8-pin isn't really going to be a concern in that scenario. But yeah, it's just one of those things where it's like, I wish it was the high current variant of the connector. And then the other really cool thing that MSI has done with this board to sort of, push it towards memory overclocking, and this is really what it's focused on. Like, the CPU overclocking should be quite good, but the priority with this board is the memory overclocking, because ITX motherboards naturally have a memory overclocking advantage because they don't have 4 DIMM slots. So by having 2 DIMM slots, you end up with shorter traces, and also just the fact that you get rid of the extra DIMM slots themselves. Add a whole bunch of negative parasitics to the memory traces, because the traces are shared between the DIMM slots on a given channel. So by eliminating the extra DIMM slots, you actually get a memory overclocking advantage. And MSI, so with ITX boards, if you have a well laid out memory topology, along with the 2 DIMM layout, like along with the fact that you have 2 DIMMs, ITX boards are naturally really good at memory overclocking. Now, MSI decided to really push this advantage to the limit here, because not only, do we have the whole ITX 2 DIMM motherboard benefits, this is on SMT DIMM slots. So we can see that you basically have paths coming out of the memory slots all along the slots. And then on the back of the board, you don't see any of the pins coming through, and this further improves the parasitics of the DIMM slots. So basically, better memory overclocking because of the type of DIMM slots that MSI is using here. And then also, this board is on a 10-layer PCB, but the thing is, with ITX boards, you naturally have pretty high layer counts. Like, even the cheap, this is a $270 Z490 board, and the easiest comparison I can think of off the top of my head, because I'm pretty sure a certain Z390 board does have 8 layers, and it's like half the price of this, but I'm not 100% certain, so I'm not going to make that comparison. But for X570, like, you have $200 ITX boards with 8 layers, and even lower cost ITX boards will often have 8 PCB layers, because ITX boards just require more layers in order to fit all the necessary features and circuitry that they come with, because you can't just go around things anymore because the boards are so small. right? Like on an ATX board, if you want to connect something on, say, this end of the board to something down here, well, you can potentially just kind of go around everything on the edge of the motherboard, right? But on a board like this, well, like this right here is the PCIe 4.0 clock gen, or PCIe 4.0 compatible clock gen for this motherboard. So, like, that normally wouldn't live here. On an ATX board, that would be between the PCIe slots and the CPU socket. But here, you have the M.2 slot down here, there's the chipset down here, like, you can't fit this down there. So, yeah, and because of that, ITX boards naturally have high layer counts, but 10 layers is actually higher than what you normally see on an ITX board. So that's just MSI. Part of it's going to be like fitting all of the functionality that the board comes with. Part of it is also just like, well, if you have more layers, you can do a better memory layout because you're not trying to squeeze all the memory traces onto as few, like you have more space to lay out the traces across. So yeah, this board is very, very focused on memory overclocking, and it could easily be sort of one of the best Z490 memory overclockers out there. So I'm really excited to get to testing it because MSI has actually sent me a review sample of this board. So yeah, I can't wait to do some like, well, mostly focus like 2x16 testing, 2x32 testing. Actually, multiple different sets of 2x16 testing because I have some kits that I want to try in this. But yeah, so I'm really excited to mess with this board because it should be an absolutely amazing memory overclocker. Anyway, so that's kind of the non-VRM things about this board that are cool. Now let's talk about the VRM, which won't be cool even though it is very efficient, and that's like why the fan is in the VRM, like why we have the fan cat out in the rear I/O. And I actually think like putting a fan on an ITX board like this, it's a good design decision. Putting fans on your giant ATX board, pointless, very pointless, unless, of course, you design a VRM that's so inefficient that you actually need the fans, in which case you should have just built a better VRM. And then there's like MSI's approach where like the Z490 Unify has VRM fan, like has a fan for the VRM when it's like the VRM barely even needs the bloody heatsink. Why is there a fan? Well, this, unlike the ATX MSI boards, will actually potentially like benefit from having the fan, because the problem with ITX motherboards is like, well, the VRM, it's very small. And so even though this VRM right here is actually very efficient, it's still going to get hot because all of the heat it produces is concentrated in such a small amount of area. So what we're looking at here is, yeah, that's a fun layout down there. So that right there is VCCSA, and this board's crowded. Man, what the hell is that A? So that's VCCSA. This right here is iGPU power, because you might want to use the board, might want to use the iGPU on this, and then that'd be a very weird application for a Z490 ITX board. Like, I feel like if you're going to be using the integrated GPU on an ITX board, you might want to get like a Ryzen APU instead, right? Because that's a significantly better iGPU. But anyway, you do have iGPU power here, and then the rest of this is, of course, all vCore. And this is just a true 8-phase, which is pretty neat because there's no doublers, and so the transient response should be pretty good because you just have the controller going directly to every single one of the phases. But the other thing that sort of helps ITX boards with transient response is just how the VRM is jammed right up against the socket. Now, the problem with this is that when your capacitors, especially this capacitor bank right here, can sometimes cause compatibility issues with heat sinks because these are tall, and they're actually like significantly taller than the actual mounting mechanism. So some coolers, like I've mostly run into this with AIOs, where in certain orientations, the AIO will not fit because of the capacitors right next to the CPU socket. And so I'm kind of surprised that MSI didn't go for SMD capacitors, but at the same time, SMD capacitors are significantly more expensive than the through-hole ones. They also give you better transient. Like, I would have preferred through-hole ones, but the thing is, ITX boards, I mean SMD caps, I would have preferred SMD caps instead of the through-holes. The funny thing is, ITX boards, even with the through-hole caps, actually do really well just because the power plane is so extremely short. So you just have less impedance between the capacitor bank and the CPU socket because you just jam the capacitors right up against the socket. So that's kind of neat. And then, of course, you know, the fact that it's a true 8-phase just further helps with the transient response. And so, yeah, I have high hopes for the transient response capabilities of this motherboard. Also, MSI does actually have the CPU socket fully populated with capacitors. You know, we can see that on the back as well as at the front. And these are just 0603 multi-layer ceramics. And this looks a lot like basically, well, ignoring the controller and the really nice power stages, this looks like, capacitor-wise, this looks a lot like the Z390 ITX from Gigabyte. Or even MSI's own ITX, but that one was missing a bunch of capacitors in the socket. And yeah, the Z390 ITX from Gigabyte actually did really well on transient response. It also ran ridiculously hot, which is not great, like, which is the main reason I wouldn't recommend that board to people, but yeah, like, the capacitor configuration here looks like this should perform very, very well in terms of voltage regulation. And so the controller, which I've failed to mention for a while now, is the ISL 69269, which very common controller on Z490. And of course, it's running in an 8+1+1 configuration here, which is how we get the 8 phases, the iGPU, and then the VCCSA. For the power stages, we are looking at a whole bunch of ISL 99390s. And these are 90 amp smart power stages. Oh, well, for the power stages on iGPU and vCore, we're looking at ISL 99390s. VCCSA is a ISL. I don't know why I bother with the part manufacturer name, but well, whatever. 99360. Like, the thing is, with Intersil parts, like, they just start with ISL, so it would be like 99360 from Intersil, and I'd assume if you punch that into Google, it would come up with the ISL 99360. But anyway, that's a 60 amp power smart power stage, and you know, like, obviously VCCSA isn't a high current rail, so you're not gonna, like, there's no need to use a 90 amp smart power stage on it. There are definitely boards out there that have 90 amp smart power stages on VCCSA. I think it's honestly kind of pointless, but yeah, and you know, MSI agrees with me on that. It's like, there's no reason to use a 90 on the system agent rail. It just doesn't pull that much current. But and so that's why they're using these 60s. But the thing is, like, a lot of the vendors that don't have a ridiculous power stage on the VCCSA, well, you wouldn't see like even the 60 amp power stage is like a smart power stage is a lot for VCCSA. So yeah, the VCCSA here is still very, very powerful. But yeah, so that's the power stage configuration. And the smart power stages, they're called smart power stages because they have built-in short circuit protection, over current protection, over temperature protection. They have more accurate current monitoring built into them than what you would get on like past generations of power stages. And in fact, if you go look at like DR-MOS components, they just don't do current monitoring at all. They also have built-in temperature monitoring. And yeah, they basically integrate a whole bunch of functions that normally would have to be implemented through external circuitry or features within the controller. Well, these just kind of do that on their own, which is pretty cool. And that's why they're called smart, because they're smarter than normal power stages. Or DR-MOS components, which are basically just a driver and 2 MOSFETs and therefore not smart at all. Anyway, so the other thing with the smart power stages is that they are ridiculously efficient. And with the 90s, the thing with the 90 amp smart power stages is the nominal current rating is a bit misleading. The 90 amp smart power stages aren't massively better than like 70 amp smart power stages. And what was really funny is that if you like, well, with most of the documentation for the really high current parts, like say 60 amp parts normally have their efficiency curves end at 55 amps. 70 amp parts normally end at 60 amps. 80 amp parts normally end at 60 amps. 90 amp parts also normally end their efficiency curves at 60 amps. And these are slightly more efficient than 70 amp parts, but it's not like a huge difference. So like, these are still top of the line power stages. In fact, the very best that Intersil makes. But the thing that I'm trying to point out is like, that 90 sounds a lot bigger than it actually is in sort of real, like the impact of these being 90 amp power stages is a lot smaller in practice than you would think it is compared to something like a 70 amp smart power stage. But Anyway, this is as good a VRM as you're going to get on an ITX board, as really you're basically like, I'm not aware of any ITX board going for anything more than like 8 phases or 8 power stages, and then either 70 or 90 amp smart power stages for the components. So yeah, this is as good as it gets, and it's pretty good for how good it gets. So for 1.2 volts output voltage and 400, is it 400? No, 500 kilohertz switching frequency for these. 500 kilohertz switching frequency. You'd be looking at the following efficiency. So 200 amps output, which is on the low end of what a 10900K can pull. This VRM will produce about 17 watts of heat. And because this is an 8-phase, you do need a heatsink for that, because that is over 2 watts of heat per power stage. And so, yeah, this is going to get pretty hot just because this is very dense, right? Like, this is great efficiency. Like, 200 amps while producing only 17 watts of heat, that is incredible efficiency. But it's still going to be hot because you've only got 8 power stages, and they're all jammed right next to each other on, you know, tiny little ITX board. Like, theoretically, if you if you stretch the board out and basically put like a lot of sort of empty space between the power stages and between the inductors, you could probably get it down to the point that the PCB would be enough of a heatsink that you could dissipate 2 watts per power stage. But in an arrangement like this, yeah, no, you can't. So in this scenario, you definitely need heatsinks for even just, you know, 17 watts of heat. And then 300, oh wait, nope, 250 amps, because of the fact that this is so thermally dense. 250 amps output, this VRM is going to be producing about 24 watts of heat, which is still good efficiency. At this point, we're starting to, you know, have worse efficiency than some of the really high-end Z4, well, like the high-end Z490 boards out there. But still, this is a respectable, you know, efficiency for this much current. The thing is, 24 watts spread across 8 power stages, that's 3 watts per component. You need heat sinks. You really need heat sinks with that kind of heat density. And then once you hit 300 amps output, this VRM is going to be putting out 33 watts of heat, which, just for fun, that is still 91.6% efficiency. So that is not a inefficient VRM. It's just 8 phases. Like, that's 4 watts per component. At this point, I would very much assume that the fan is necessary, just because you can't, like, this is too small, right? Like, it's not even a problem of, like, MSI could have used better parts. No, this is just too small. You can't find, like, you can't buy better power stages than this. You can't fit more power stages than this onto the board unless you know, like, maybe you could sacrifice the Thunderbolt 3, throw out the Wi-Fi, and then make the board completely unacceptable to most users, and you could finally fit a VRM that can do easily 300 amps output. But that's not a practical way of building an ITX board. So the solution is, of course, just heat sinks and then force airflow through them, because heat sinks running passively are horribly inefficient because the convection, which is the whole hot air rises, is really slow. So, you know, fans much faster at moving air. Even tiny little, like, 30 millimeter fans are far, far better than no forced airflow, because relying on hot air rises, depending also how cramped your ITX build is, like, well, if your ITX build is really cramped, you're probably not going to be able to cool 300 amps of CPU power consumption, but still, the fan is a good idea. Because even if you weren't in the most cramped build, well, if I had this board on a test bench, I would just put a fan on top of the VRM heatsink anyway. But yeah, if you're lazy about that, then because I could totally see people using, like, I'd use this board on a test bench for, like, memory testing, right? Because the memory overclocking on this is incredible, or should be incredible, and yeah, like, in that scenario, you know, you might be hammering the 10900, like, you might be stress testing with, like, LinPack or something to prove that it's actually bloody stable. And yeah, the VRM would get very upset about that very quickly if you didn't have any forced airflow over it with a 10900K. So yeah, if you're on like a 10600K, you're never going to get past, like, 10600K maxes out at around 200 amps, or you can go a little bit past that. And a 10900K, 10700K can go around 250, but 10900K is, like, you can technically go over 300. And so yeah, you definitely need the active cooling on this board is definitely a good idea. And let's say you wanted to bench on LN2 with this board. Well, 400 amps output, this VRM is going to be kicking out 53 watts of heat. The heat sinks are very much not optional. And though the cool thing about benching ITX boards on LN2 is that the boards are so small that if you don't have like a socket heater, the whole board will freeze over. Which is potentially bad for your memory sticks because there are some memory sticks that are very sensitive to low temperatures and they stop working if they go below like 0 degrees. Or actually, I've heard of memory sticks that stop clocking properly at even like 5 degrees, where they're just like cool to the touch but not yet frozen. And it's like, yeah, that's already bad enough for some sticks. Yeah, like if you let the board freeze through, then, you know, you can rely on the fact that the VRM temperature is starting out very, very low to help you finish the benchmark before it really overheats. And then 480 amps, because again, the data sheet stops at 60 amps. Like, yes, this is a 90 amp smart power stage, but even Intersil themselves acknowledges that nobody is realistically going to be shoving 90 amps through one of these, because even if you have like the thing is, we're already at just 91% efficiency at 300 amps, which is, what is that? That's a little under 40 amps per power stage. Well, at 90 amps per power stage, you'd be looking at like 80% efficiency or something, or 85% efficiency or something. But even if you were doing 90% efficiency, 90 amps at 1 volt translates into like 9 watts of heat per component. Not a practical usage scenario. So yes, these are nominally a 90 amp smart power stage, but nobody is ever going to actually want to run 90 amps through these. They are going to get way too damn hot. But they can do it. If you somehow had enough cooling, you could do 90, but you shouldn't. It's not a good idea. 480 amps, which is where the data sheet tops out, would give you about 78 watts of heat output. So there, it's really going to be like, I hope the heat sinks have enough thermal, like if the heat sinks are frozen enough and they're heavy enough, then yeah, you should be able to finish your benchmark before the VRM overheats. It's kind of the issue with having just an 8-phase. And the funny thing is, this is better than like the VRM you'd find on some X299 boards, but yeah, this is pretty borderline. 10900Ks pull a hell of a lot of power. And unfortunately, like, you're just not going to get a better VRM on an ITX board because ITX boards are too small. I really, like, I still wish that MSI would just give us, like, a stretched out version of one of their ITXs. Because the thing is, this, like, with the Z490i Unify, they are really pushing the memory overclocking to the limit, right, with the SMT DIMM slots, with the 10-layer PCB. But even the Z390 ITX from MSI, the Z390i Gaming Edge, that thing was really good at memory overclocking. Like, surprisingly so. Like, I didn't have high expectations, and then I got it, and I was like, oh my god, this, like, when you wanted to do high frequencies, like, there was very, like, it was up, like, keeping up with boards 2 to 3 times the price. And, you know, like, and there I already wished that they would just give us like an MATX version of the ITX board where they'd keep the memory layout, so just 2 DIMM slots, but bigger VRM. And with this, it's just kind of like, I really wish they would do a 2 DIMM MATX board with a bigger VRM. But I can totally understand why they don't, because the thing is, having, like, unfortunately, seeing a, like, ATX or MATX motherboard with only 2 DIMM slots tends to be a massive turnoff for consumers who know nothing about memory overclocking. So they're going to buy their 4 DIMM motherboard, stick 2 memory sticks into it, and probably forget to enable XMP anyway. So, yeah, I guess, you know, like, why am I like, how can I be surprised, right? So, yeah, but it's really cool what MSI is doing with this board, especially if you're into primarily memory overclocking and not so much into, you know, hammering the CPU, because, yeah, it's nice. Like, the thing is, if you're just doing, like, water-cooled benchmarking, you shouldn't run into any issues with this VRM, assuming you give it enough airflow, but, yeah, if you decide to, you know, like, taking this sub-zero, you might have to let the VRM cool down between benchmark runs, essentially. Like, that's the main thing, is, like, you might have to just sit there and wait for it to cool down after you finish Cinebench or something. Like, you could still totally do it, though. So, which, again, like, considering the price point of this board is really, like, this is a $270 ITX board. Like, that is Like, that is a very interesting option, in my opinion. Just being able to get like an ITX board like this and get the really good memory layout, and then also like the support for LN2, because this board does have all the necessary voltage regulators for Sub-Zero. I'm not going to try to highlight them because this is so dense that they're annoying to point out, but yeah, this can go Sub-Zero. It's pretty much designed for that. Also, that's pretty much it. We've got single-phase memory power, but I've mentioned, you know, plenty of times in the past, you don't need to, like, memory power just doesn't make that much of a difference. It's not about how you power the DDR4, it's about how you connect it to the socket, and, well, like, you're going to have a hard time finding a board with a better memory topology than this, at least in, like, like, in MSI's motherboard, well, I've screwed up that sentence. Just, yeah, you're not really, like, for a 2DIMM motherboard, like, you're going to be hard, like, you're not going to find a better option from MSI, in my opinion. So, yeah, I'm really, really excited about this board because it should be absolutely amazing for memory overclocking, which, you know, some people do just for fun. I mean, I technically do memory overclocking for fun. It's one of the bad ideas I get when I'm bored. It's like, oh, I'm bored. What should I do? Oh, I'll go do some memory overclocking. And then I just end up really frustrated. Anyway, so yeah, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. There's a link to that down in the description below as well. So, yeah, that is it for the video. Thanks for watching, and also thank you to MSI for, you know, well, the pictures, and also sending over the board so I can test it. Because yeah, this is a Z490 board that when I heard it was announced, like, I got really excited when I heard that they were doing this board, because I heard about the SMT DIMM slots pretty early on, and I was like, oh my god, I need a chance to test this because this could be really, really cool. So yeah, thanks for watching. Goodbye.